Good morning, everyone. Firstly, I'd just like to say apologies if you had some issues logging this morning. I'm afraid that's what happens with technology sometimes, but we've got absolutely amazing attendance now, so it looks like everybody's now in. So good morning, and thank you for joining us for a live talk with SEM Ambassador Stephen, who is a Professor of Astronomy in the School of Mathematical and Physical Sciences at the University of Sussex. It's great to see so many schools joining us today, individuals, and we're sure you will enjoy this webinar. To celebrate World Space Week, Stephen will excite you with in-depth knowledge about two amazing telescopes, one very new and one not so new, but very much grabbing news headlines. You'll also hear about Stephen's own career path and the routes he took to get there. Please feel free to ask any questions by putting them into the chat, and Stephen will aim to answer as many as he can at the end of his talk. So that's enough from me. I will hand you over to Stephen. Good morning, Stephen.
Morning. Thank you, Lisa. Good morning, everybody. Nice to maybe not see you this morning because I'm just staring at my computer screen. So today I'm going to talk about two relatively new telescopes, so Euclid and JWST. But before I do that, I was just going to introduce myself very quickly. So I'm originally from up north, so Leeds in Yorkshire. And actually, my interest in astronomy and physics was actually first driven by playing a computer game. So this is a nice excuse if you want to start playing computer games. And in particular, I played this game called Frontier Elite 2 in the mid-1990s, which kind of gives an indication of how old I am. The reason why I played this game is that you could fly around in a spaceship, you could do various things. But what was really nice about this game is that they tried to actually put in real physics, real astronomy. So they actually imagined a real galaxy containing real solar systems. And so you can see here an example of our solar system built into this game. So this really kind of captured my attention at the moment. At the time, and so this is one of the things that really got me into physics. Now, technology has evolved, and so today there is a new version of this game which you can clearly see looks much better. So this is now Elite Dangerous, but the same kind of philosophy is there as well. So just building on this a little bit more, so after I completed my time at school, I then went to the University of Durham, where I studied physics and astronomy. I then got a PhD from the University of Cambridge in astronomy. I was then a researcher at the University of Oxford for a few years before moving down to Sussex now about a decade ago. And while I've been at Sussex, I've steadily made my way through the department. So I started off as a lecturer, and I was recently promoted to professor, which is kind of the top level that you can be at the university without being in charge of the university. At the same time, I'm also head of astronomy. This is kind of a role, not really my title, but this is what I do as well. And so I mentioned here that I'm currently head of astronomy, and I also serve as the director of outreach and public engagement. So this means I do a lot of talks, I run exhibits, I run science fairs and things like that. What I really like about my job is that it's really very varied. So I do a mix of teaching, of research, administration, but also public engagement as well. Okay, so my job routinely involves, designing computer software, writing articles, making and delivering presentations, organizing people and travel. So it's really great. You never really get bored in this job because there are so many different things that you can do, so many different directions we can take things. Okay. Fundamentally, I'm a physicist, so my background was in physics. So physics, if you don't know, is the science of matter, and it involves studying matter and its fundamental constituents. So today we know that the universe is made up of atoms, and atoms themselves are made up of other particles. At the most fundamental level, we have things like quarks and electrons. So physics also studies the behavior of matter through space and time, and its main goal is to really understand how the universe behaves. Now, physics is a really expansive field. There are lots of different types of physics. So you go all the way from things like astronomy, atmospheric physics, geophysics, materials physics, and then to areas of technology as well, like nanotechnology, which is very big at the moment, and quantum technology, which is an emerging field. So it really is, a huge field, and there's lots of different areas that you can study. But it's all really linked by, trying to understand how the universe works. Okay. So what can you do with a physics degree or an astronomy degree? Well, a physics degree actually builds up skills that are really heavily in demand. So things like being able to program, being able to solve problems, being able to present your work to other people. And so this opens up a really wide range of careers. There's many more that I'm listing here, but these are just a few of them. So you could be a research scientist, or somebody who's trying to push the field forward. You could be like me, a university lecturer, where you're also teaching people. You could be an engineer, where you're implementing the most recent advances that we've made. And people who go into engineering from physics, they're often working really at the cutting edge of the state-of-the-art advanced technology. You could go into software engineering or data analysis, right? That's a really massive growing field at the moment. You could go into finance. So finance is really, the skills that we develop are really in demand for the financial sector. You could be a science communicator. You could tell people about science, or you could be a teacher, or you could even be an astronaut. And the reason why I mentioned astronaut is that the person on the right here, this is Rosemary Coogan. Rosemary was recently selected as one of the first of a new cohort of astronauts. So that's me on the left-hand side, and the reason why we're both together is that Rosemary was one of our students here at Sussex. So we're tremendously proud of Rosemary's achievements, and we're going to watch her in the future. Hopefully, in the next couple of years, she will be going to space. But at the moment, she's just begun her training. Okay, so what I'm really going to talk about for the rest of this talk is really these two telescopes. It might be that some of you listened to me talk last year when I talked about just the James Webb Space Telescope. Well, today I'm going to add in a little bit extra about the James Webb Space Telescope, but also introduce another telescope called Euclid. So the James Webb Space Telescope launched in late 2021, actually on Christmas Day on 2021, whereas Euclid actually launched only a couple of months ago. Both telescopes have actually very different capabilities and scientific objectives that makes them really complementary. So actually, these two telescopes working together is much more powerful than them working individually. And so I'll mention some of that. But first of all, the older one, JWST. Less than 2 years old, but still the older of the pair. So JWST is the scientific successor to both the Hubble and Spitzer observatories. As I mentioned, it was launched on Christmas Day in 2021, and it's actually been observing the universe since July last year. So a little bit over a year now, it's been observing our universe. It is a collaboration between NASA, obviously the American Space Agency, and then the European Space Agency, which is our space agency, and as well as the Canadian Space Agency. And in addition to these three big organizations, there's hundreds of universities and thousands of individual scientists who are involved in this project. So it really is a kind of global effort. Although it's led by NASA, there is strong, contributions from the rest of the world as well, in particular Europe, and in particular here in the UK, where we built one of the cameras that is currently on the telescope. So as I mentioned, there's a huge number of people, who have contributed to JWST, and these are not just astronomers. So in fact, there's a whole massive team of people who enabled JWST. So obviously, first of all, there are the astronomers. These are the people who, said why we want this and are actually going to be using it on a day-to-day basis. But in addition, there was the engineers who helped design and build the telescope, the technicians who, again, built the telescope as well and maybe maintain it. There were software engineers, right? We need software engineers to allow us to control the telescope and get the data, right? We have administrators. All of these big teams of people, need people to control them and direct them. We need digital creatives, so we know that we're going to try and share some of the results from this telescope with the rest of the world. Many of the pictures that I'm showing you do not come from the telescope the way you're going to see them. So we need people who've got, skills with software like Photoshop to actually, turn them into the creations that we can share with people. Okay, so it really is a project where, there are many, many ways of getting involved. So as I said a few minutes ago, JWST is actually the successor to both Hubble and Spitzer. So you can see JWST, Hubble and Spitzer on this slide. This is now showing you them all, the actual relative size that they are. So you can immediately see that JWST is much, much larger than its two predecessors. In fact, if you just highlight the size of the primary mirror, this is the most important element of the telescope. You can see that JWST is around 6 times larger than Hubble and around 50 times larger than Spitzer. And whenever you make a telescope which is this much larger than its predecessors, It's going to be, viewing the universe in a completely new way. But in addition to just being bigger, JWST also has a range of other capabilities which these two previous telescopes didn't have. So for example, JWST has extensive spectroscopic capabilities, right? And this can actually impact the scientific questions we can answer. And just to be clear here, spectroscopy is simply the science of splitting light into its component wavelengths. So what you're seeing here in this image is a simple prism, right? You've probably used one of these at schools many times. And what a prism does is essentially take light, or white light, which is a mix of different colours, and it splits it into all of those different colours. Now, we astronomers, we really like doing this because by doing this, we're able to examine objects in more detail and actually learn a lot more information about them, particularly about what they contain, for example. And in addition, more importantly, unlike Hubble, but like Spitzer, JWST is designed to observe the infrared. So this is light that we can't see with our own eyes. It's light which has a little bit of a longer wavelength than visible light. So you can see in this diagram here where JWST kind of covers the part of the EM spectrum. So the Hubble was designed to originally just observe in the visible. It was subsequently expanded to see bits of the UV and the infrared. Spitzer was designed to complement Hubble by just observing the infrared. And JWST comes along somewhere in the middle, kind of this gap, what we call the near and mid-infrared. And this is because we really didn't have very good capabilities in this part of the spectrum. So by studying here, we think there's lots more that we can learn. Now, JWST's capabilities allow it to study a whole range of science questions. This stretches all the way from the study of our own solar system to some of the most distant objects in the universe. So we often kind of put or group JWST's scientific objectives into these 4 areas. So other worlds, the life cycles of stars and how galaxies change over time, and then the very distant universe, so the formation of the very first stars and galaxies. So I'm just going to show you a few images that have been taken by JWST over the last year, demonstrating some of the science that we can do here. First of all, I'm going to start very close to home. So what you can see here is Neptune. So down at the bottom, you can see Neptune with a handful of its moons labelled. In this image, you can really nicely see both Neptune, but also its ring system. So it's not just Saturn that has a ring system. In fact, all of the gas giants have some form of ring system, albeit in some cases quite small. But what's more interesting in this image is Triton up there at the top. So Triton is actually a moon of Neptune. It's much, much smaller than Neptune. But despite this, in this image, Triton is actually brighter than Neptune. There is more light reflected by Triton than is reflected by Neptune. And this is because Neptune isn't very good at reflecting infrared light. It actually absorbs all of the red and infrared light, which is why it appears bluish. And so what you're seeing here is just a reaffirmation of the fact that Neptune is blue. The reason why it does this is because of what the universe contains. Sorry, what Neptune contains in its atmosphere. So the fact it's blue is telling you about the stuff that is in Neptune's atmosphere. Going a little bit further away, we have images like this. So this is a very, very special bit of our own galaxy called the Pillars of Creation. And these are big, huge clouds of gas and dust where new stars and planets are forming right now. Right, so this bit of our galaxy has been studied previously with Hubble, but this is a relatively new image taken by JWST. And the reason why this is different from what we've seen before is by looking in the infrared, we're actually able to see through some of the gas and dust in this area from which the stars are forming. We're actually able to see the individual stars forming. Now we can also zoom in onto an individual star right at the very beginning of its lifetime. And so what you're seeing here actually is a star which is just growing, right? So it hasn't become like the sun yet. It's actually still feeding on its surrounding material. And actually the material which is growing the star is coming from either left or right. Now, as the material falls onto the star, although some of it makes the star get larger, some of that material is thrown off up and down, which is what you're seeing in the bright colours here. Stars not only are born, they also die. And so what you're seeing here are the leftover remains of a star that has died a few thousand years ago. So when stars like the sun die, they leave objects like this. This is something called a planetary nebula. and this is essentially the leftover remains of that star. If we zoom out a little bit further, we can now look at other nearby galaxies. What you see here is a region of a nearby galaxy called the Tarantula Nebula. So in this image, what you're seeing is a very new collection of stars, a cluster of stars that has recently formed from all the dust and gas here. And again, by looking at images like this, we can figure out how stars are formed and how they change over time. Again, going even further out now, here we see a picture of a galaxy. This is actually a very famous galaxy called the Whirlpool Galaxy, but we're seeing it in a completely different way now. What we're seeing actually here is the dust in this galaxy glowing. So this is what you see, all this intricate structure that you can see is actually the dust glowing. This is a really nice picture because this was actually taken using the camera that was built here in the UK. And then what I actually work on is actually studying galaxies, how they change over time, and trying to find the very most distant galaxies. To study these galaxies, we use images like this. So this is what we call a deep field. This is where we take a telescope and we look at a relatively empty patch of sky and we observe it for a long period of time. When we do this, we're able to collect light from very, very distant objects, which we're seeing when the universe was much younger. So the blobs in this image are stretching back almost over the entire history of our universe. And so what me and my team do is actually to look at all of these blobs and try and work out how the universe changes over time and compare it with our models. Okay, JWST is absolutely fantastic. It is enabling so much science, but it does have a quite significant limitation. And this limitation is that at any one time, it only observes a really tiny patch of the sky. Right, so you can see here an image of the full moon, and the patch of sky that JWST sees at any one time, it is one tiny bit of the same size as the full moon. Okay, so this is really problematic because there are things out there in the universe which are very rare and are very difficult to find. And it turns out if you wanted to observe the entire sky with JWST, you'd have to take 15 million individual observations. Now, that's just not going to happen. It's just too much for JWST to do. And this is why we need other telescopes as well. If we want to map the entire sky and find rare things, we need other telescopes. So this actually makes JWST extremely limited for studying large volumes, and this is particularly the case if you want to learn about cosmology. So you want to learn about what the universe contains on the largest scales. And this is where Euclid comes in. So Euclid is a new space telescope. As I said, it was launched a few months ago, and this is actually led by the European Space Agency. So it's led by us. So this is our space agency. Right, it has some small contribution from NASA, but pretty limited. As I mentioned, this was launched in July, so you can see it launching over here. Now, Euclid is actually much smaller than JWST, meaning it's much less sensitive. So you can see, the size of Euclid on the left compared to JWST on the right. So being a small telescope, it's going to be less sensitive and have lower resolution. But the key difference here is actually Euclid has a much larger field of view. At any one time, it can observe a larger area than the moon. So this, together with its dedicated focus on mapping the sky, means that Euclid will survey, a much larger area than ever possible by JWST. In fact, over its 6-year mission, Euclid will map around 1/3 of the entire sky. So this large area and this kind of design to do survey allows us to do science that JWST can't, making it very complementary. So for example, JWST is going to make a huge map, a 3D map of all of the matter in the universe, right? Well, around a quarter of the universe. And by doing this, by making this map, we can understand what the universe contains. And so, for example, what we're trying to do here is to constrain things like dark matter and dark energy, these two big unknowns in astrophysics, which seem to make up most of our universe. We want to understand them in more detail. And by creating these big 3D maps, that's exactly what we can do. But with Euclid, we can also, by observing very large areas of the sky, find very rare things. And so things that are very rare include galaxies which are dominated by supermassive black holes. In this image that you can see, this is actually the surroundings of a supermassive black hole that was imaged a few years ago. not by Euclid, but by a different telescope. But the idea here is that Euclid, because it covers such a large area, we can use it to actually find lots of these objects. So this brings me to the end of my presentation now. Sorry it was so short and sweet, but we only have a small amount of time today. But all I want to say here, just to conclude, is that we're really at the beginning of these two missions. So JWST is likely to be with us for 2 decades. Similarly, Euclid has only just started its 6-year surveying mission. And even though that mission may take 6 years, we'll be analysing that data for probably another 10 years afterwards. And what this means is that I'm pretty sure everybody on this call at the moment could have the opportunity to work on one of these amazing projects, or maybe even build to the things that come after this, because we do have plans for what comes next, but they are going to take 10 or 20 years as well. So there really is the opportunity to get involved in these missions during your careers if you want to go down that route. And just very finally, just as a brief advertisement, if anybody is in East Sussex, particularly Lewis kind of area, we have a free science fair coming up in just over a month where you can actually learn more about some of these projects from myself and my team. And I'll stop there, Lisa.
Thank you very much, Stephen. No, carry on. It's so interesting. We want to hear more, but as we know, there isn't enough time. So thank you. All very interesting stuff. I can see that we have some questions coming in. So I'm going to hand you over to my colleague, Sophie, and she will put those to you.
Thank you, Lisa. Okay, so Stephen, so the first question that I've got through, how much does it cost to create the telescope and put it into space? I'm assuming they're talking about the James Webb. Yeah,
so the James Webb Space Telescope has cost about $10 billion US. Now, bear in mind that that's $10 billion US spread over 20 years, and with contributions from the US and Europe. So it's $10 billion spread over around 500 million people. So when you start, kind of dividing those numbers together, it turns out to not be a huge amount of money per person. And this is, pretty small compared to many other, areas of expenditure, considering that you spend over such a long period of time. Euclid is obviously cheaper. So Euclid has cost, I think, around £1 billion. And again, that's spread over Europe, and it's been spread over, the last 10 years or so and going into the future. So these things, they are expensive, right? But they're going to produce, observations and data that are actually open to everybody in the world, right? So hopefully people will, find value in all of these things. Certainly the astronomers trying to understand how a universe works, we will.
Great, thanks. So that question kind of leads on to another question here that I've got that says, how long did it take to design and launch Euclid, and how many people were involved?
So Euclid, a little bit more than 10 years for Euclid, when it was first kind of imagined to where we are today. In terms of the number of people involved, there was about 2,000 scientists who are going to be using it. But there was probably another 1,000 kind of engineers and technicians who actually helped make it, at least in some small way. So obviously you work with industrial partners, you work with ESA, who are doing lots of things at the same time. So, I think we're talking about a few thousand people who were able to contribute towards this.
Okay, that's really good today. So I've got another question here. And so someone's wanting to know, is the James Webb telescope, is it like a zoomed in lens on a camera, and the Euclid is more like a wide angled lens on a camera?
Pretty much, yeah. So you can think of it like that. So, Euclid, its optics are arranged in such a way that it does have this very wide view, and JWST is designed so it has this very deep view. So yeah, pretty much. We can't change between the two. That's just too difficult to do in the context of a telescope. Although it would be nice if you could actually build something that could do that, like, a handheld zoom camera.
Okay. I've got a question asked. So with so many stars already in the universe, how do I know when new ones are born?
So, well, we can look at images like the image that you can see there in this poster. So this is the pillars of creation. And we know that new stars are being born from these clouds of gas and dust. So if you see a star in those clouds of gas and dust, it's a pretty good indication that it was recently born. But we can also, if we look at stars very detailed using spectroscopy, we can actually work out exactly how old they are from the information that we can get from them. So you can actually, look at a star and you can almost, count tree rings and work out how old it is. This is a technique that we've been using for about 100 years now to try and work out how old the various stars are in the universe. So yeah, we can, with extra observations, work out how old an individual star is. But we can also see stars actually forming in situ, like in these clouds here.
It's all very clever and very exciting. Okay, so I've got a question from a student, I think, probably. What degree would I need to do this kind of research?
So we'll do a physics degree, and as part of a physics degree, you would often end up doing astronomy modules. So that would allow you to become, a professional astronomer. There are other ways, so you could end up doing something more engineering side or more computer science side. It is possible to, become an astronomer in those routes, although it's much rarer. But, we also need people on the engineering side. We need people who are going to build the telescopes, who are going to test them, right? That is, just as important as the people who are using them. And obviously, in that case, you want to do things like engineering science or computer science. So there are, multiple ways of actually contributing to these huge projects.
Okay, so it's lots of different varied routes and ways that you can contribute, so that's really good. So I've got a question here. Could the telescopes find alien life?
Yes, so actually this was one of the reasons why JWST was created. So it's one of the science goals of JWST to, examine planets outside our own solar system that are still relatively nearby and try and work out what their atmospheres contain. So we've been doing this a lot recently, or the astronomers who work on that area have been doing this a lot. And so we can look at a planet which is around another star and we can tell you whether its atmosphere contains, things like carbon dioxide or water or oxygen. And so JWST has the power to potentially see the signature of life in these planets. Now, when I say life, I'm not talking about, aliens who are going to come invade. I'm talking about things like plant life that changes the chemistry of the atmosphere. And in fact, there was a very intriguing result only around a month ago where there's a very, very tentative evidence that we've discovered a planet which has some very unusual chemistry in its atmosphere, which might be an indication of life on that planet. It's still very early days, though. This was picked up by the BBC and a handful of other media, but it is a very, very tentative result. There's nothing confirmed yet. But the point is that JWST has, this potential to do this, and that will obviously be, one of the greatest discoveries of all time. We realise that, in fact, there is life elsewhere in the universe, even if it's only, basic life like plant life.
Okay, so I've got a question through. How does the telescope, I presume this is both telescopes, send the pictures through back to us on Earth then?
Yeah, so both telescopes have essentially a communications antenna on the back, and they broadcast, the data, and then that data gets picked up here on the Earth, typically using something called the Deep Space Network, which is a really fancy way of saying just a collection of very big radio dishes, very big satellite dishes, which are dotted around the Earth so they can always stay in communication with the telescope. And then once they get there, they go to NASA or ESA, who do some processing of them, and then they just put them on the internet. And then you can just download the data from the internet. So the way that I interact is that I go to a website and I download the data I want to look at, which is kind of quite boring because in the past, before we had such a powerful internet, you used to have to get like images sent to you on data tapes or data disks.
Okay, so I've got another question. How many stars would Euclid be able to map over its 6-year journey?
So in terms of galaxies, we're talking a billion galaxies, maybe even more. And then each one of those galaxies, you know, contains millions or even billions of stars. So if you're asking the question, how many stars is Euclid going to see over its journey, then really it's going to see, you know, billions times billions. So that's just kind of a ludicrously large number. So then you're talking about a million trillion. I actually can't even remember what that number is. Now, of course, in most of those galaxies, we don't see the individual stars. We just see the kind of all the stars merged in together. But yeah, Euclid will see, you know, more than a billion galaxies over its mission.
Okay, so I've got a question here from a student asking, do you think there is life on other planets?
Well, given what I just said about how many stars there are in the observable universe, and given that we've discovered planets, you know, on average around every single star, it would be a big waste of space and very odd if there wasn't life else out there. At the same time, I don't think that life has visited us yet, right? I don't kind of believe there are little green men amongst us, but I would be very, very surprised if there wasn't, you know, life somewhere else out there in the universe. The question really comes down to is how rare it is. You know, do we only have one example of life in each galaxy, right, which would be very lonely, or is the life more abundant than that? You know, these are big questions. These are questions that we're just going to start answering now with JWST.
Okay, so it's quite an exciting future and things to come, definitely, with all this new technology. So as it's now 9:14, thank you. I think it's time we have to finish, unfortunately, although I'd love to keep chatting and learning more and more because it's a really interesting topic, and I'm sure our students and schools think the same. But unfortunately, we have to finish. So thank you, everybody who's put questions in the chat, and thank you for everybody who's been listening. I'm just going to hand over to Lisa now, just to finish off.
Thanks, Sophie. Yeah, I agree with you. You know, what an industry to be in within the space industry. So thank you, Stephen, for this most informative and interesting talk. And as Sophie said, we're sure that our audience will be inspired to learn more about careers within the space industry. So thank you to you, Stephen, and thank you to everyone who joined us today. And enjoy the rest of World Space Week. Take care, everyone. Bye.
Thanks. See you all.